Okay, can everybody hear me right now? Okay, good. Hello everyone. My name is Michael, and I'm one of the TAs, and I'm currently a master's student, like under EC department, majoring in machine learning and data science. Um, I'll be holding like office hour on like Wednesday and Friday, and I'll be holding discussion sessions on Thursday from 3 to 3:50 p.m. So feel free to come to my office hour if you guys have any questions in terms of the course materials or the homeworks materials. So let's just wait a few minutes until everyone gets in. Okay, I'll right now upload a file in the discussion the chat window for the material that we're gonna cover today. So can anyone tell me like what you can get access to the file? It's a PDF file, discussion 2. Um, can anyone hear me right now? Like I didn't see any responses in the chat. Okay, perfect. Okay, let's move on. So before we start discussing our today's material, like I'm gonna like just illustrate some of the policies that we have. So first about the homework 0, I think it's due today. And then about some of the grading policies we have, like for like the true or false questions, you're not required to write anything. You're not required to write anything uh, uh, to prove anything about true or false questions. But for the rest of the questions, we hope to see like you write down some of your thought process, and then we will not like rigorously follow. Just one second. We'll not rigorously follow like the syntax or the language you use, but we will definitely take a look at your thought process. So for me, like as long as your thought process is correct, we will just give you full credit. And about like the question policies that we have, like so during the office hour, and then during the office hour and the I'm sorry, during the office hour and the discussion section, anything related to the homework problem, I'm not allowed to give you guys the answer explicitly. I'm only allowed to provide you guys with the hints and some tips, and some of my thought process. And if you still have any questions, just come to the office hour, and we will have like a deeper discussion about your questions. Okay. So during this discussion session, so if anyone has a question, I hope like everyone can mute because we're at an online version of this version. So I hope everyone can mute. And if you have a question, just raise your hand, and I will unmute you, and you can just tell me your question. What your question is? Okay. So one of the other like question we receive on the Piazza is about LaTeX. Some students are asking like for the homework like how to use LaTeX to write homework, and the LaTeX is like strongly recommended by the professor, and we hope that everyone can use LaTeX. But if you're really not comfortable with this tool, since like LaTeX is really a strong tool in terms of mathematical expressions. But if you're really not comfortable with this tool, like you can use like other software such as Markdown or just handwritten homework instead. Yeah, homework 0 is due. It's due tomorrow night. Oh, I'll check it. I'll check it later. And I think homework 1 will be released right after the deadline of homework 0. So it should be in a couple of days. Yeah. And okay, so are there any questions in terms of like the first part is, are there any questions in terms of like the homework 0, anything about the materials, or just the materials, the layout, or anything related to the homework 0? Or like, do anyone like have any questions in terms of the comprehensive quizzes? Since right now is a good time to speak it. Let me see whether we have any hands. Okay, so I think we're all good with homework 0. Yeah, homework 0 is just like a calibration. It's more like a calibration homework to test whether you understand like the materials, the prerequisite materials of this course. So like let me just try to upload the file again, because some of you guys may enter. Just a second. I just uploaded the discussion material again in the chat window, so download it and we'll get started. So let's take a look at the question number 2 first. Let's take a look at question number 2 first. It's actually a multiple choice question. I'll give you guys about like around 3 to 5 minutes to take a look at it, and I'll make a poll here to see. I'll make a poll here for you guys to answer the question. We'll be back in about like 3 or 4 minutes. For who just joined this section, I uploaded the discussion material in the chat window. I'm not sure whether you can receive it, so I would just send it again. And we are currently looking at question 2, and there's a pool here. Yep. Okay, I will just wait 1 minute or another. I see 8 out of 10 have finished the question. Okay, I just stopped the poll and let's take a look at the result here. And the answer to this question is actually A and B. And it's actually for, I see like 5 out of 9 chose A and 3 out of 9 chose B. Yeah, the correct answer is actually A and B. And for here, like C and D actually can be like easily rejected because like we can easily find like a counterexample to disprove the statement. So like if we like choose like R of 4, like R of 4 is 2. I'll just write it down. R of 4 is 2, but it doesn't apply with C, while R of 6 is 3 and it doesn't apply with D. So like for A and B, it's quite intuitive. Like if we take a look at the structure of this question here, if n is larger than 1, then we recursively call this and then we print out hello world. So we'll actually get a like intuitive idea that like this algorithm is under big O notation, under big O of log n to the base of 3. So since like O of n actually dominates O log n, so A is correct. And like for B, like we can actually find another like intuitive answer, like intuitively. Just a second, someone is entering the room. We can like find like another like easy way to prove it. Since this is like a multiple choice question, we're not we don't require you to strictly prove it. So like there's like a quick transform from log 2 to log n to the from base of 3 to the log 2 base of 2. Just a second, someone's entering the room right now. Yeah, just this equation here, log 2 of n equals to just very simple equation to transform a logarithm to the of base 3 to logarithm of base 2. And here this is a constant, so I think like proof for B is not very hard, but like the question here, we want to go deeper a little bit. We want to prove actually that C and D are actually upper bound and lower bound of R of n. And if we write it like more strictly, it is that R of n is larger than plus 1 and smaller than. So I will basically go through the proof, like the logistic of proving this statement, and it also shows like the one of like our grading policy, like what kind of thought process we want you to show in your own homework. So let's get started. Just try to clean it up here. So this is what we want to prove. And if we take a look this, if we first we assume, if we assume that n equals 3 to the power of k, then like can anyone tell me how many hello world shall we see in this algorithm? Like we just assume like n is 3 to the power of k, and how many? Yeah, it's true, but like log n to the base of 3 is actually k, so we'll just say k plus 1. Yeah, you're correct. We have k plus 1 hello world here, so this is our, we'll just say claim 1. Let's just circle it. So right now we want to transform this statement to a more like provable or solvable statement. That is for all in this range, that 3 to the power of k less than n, and n is less than 3 to the power of k plus 1. Well, this should be for all the n in this range. We have we want to transform this like statement to a more provable statement that we can apply our tools to prove it to this statement. This is so I would just like provide like a basic intuition about why these two are equivalent, because for all n in this range, since like the algorithm is like this, we apply, and this is the algorithm. For all the n in this range, they should all have like the same number of hello world printed out. And that means these two statements are equivalent. Yeah, so basically like we actually successfully transformed the previous statement to another more provable statement. And we can actually apply our tool, which is induction, to prove that this statement holds. And let me show you guys a step by step. Like this is just you're not required to do this, but if there is a question related to induction, this is the kind of thought process we want you to show in your homework. So let's define P of I. P of I is n such that this is the P of I. Right now, like the first step for induction is to prove that the base case is correct. So I want to prove like P0 is correct. Usually the base case is always correct. Like we don't need to spend a lot of time doing that. Like P0 is, let me see. So for P0 is definitely true for all n such that 1 is we'll just basically print out the hello world twice, 2 times, which is in this range. Pretty simple. Right now, let's go through the induction step. So induction step is we assume that P0, 2, P of K is true. And we want to induce that Pk plus 1 is also true using the induction hypothesis we have, which is this. So how can we do that? Let's see what Pk plus 1 is. Pk plus 1 is for all n such that 3 to the power of k plus 1 less than So this is basically, let me write it with another color. This is Pk plus 1. This is Pk plus 1. And how can we prove it? And so one thing is like, R of n equals to R n divided by 3 lower bound plus 1. This is because the recursive step of this algorithm we have here. Let me circle it. We have here. This is the first step of our proof. And then given that we can easily prove that this is between and by the induction hypothesis we have where Pk is true, that also means that R is less than K plus 2, larger than K plus 1. Yeah. So then we can easily show that since R of n equals to this, and we have we really successfully proved that this holds, so we can easily prove that R of n is less than K plus 3, larger than K plus 2. So this is the final step of the induction and the proof of induction. Using this principle of induction, we can get Pi is true for all I using induction, and we can successfully prove that C and D are actually the upper bound and lower bound of the number of times that this function prints hello world. So far, any questions about it, or about the proving step or policy, or anything we have, anything we cover so far? The answer is A and B. A and B are actually because C and D we can find a counterexample. C and B here, please be careful that C and D here are not actually big O notation. It's just exact number. So C and D we can find no, this is not for homework 0. This is just the discussion material we have. If you have any questions in terms of homework 0, we can discuss maybe after this discussion session. Yeah, the C and D are actually the upper bound and lower bound, not exact runtime, because the number we can find counterexample to show that the exact runtime. It's not runtime, it's the number of times this function prints hello world. We can find counterexample to show that this is not correct. Basically the statement is too definite. It uses an equal sign. In the multiple choice question, an answer with equal sign usually means it's wrong. That's the case. Okay, so let's move on to the next question. I'll just make a new page here. Prove or disprove like there are an even number of odd degree vertices in an undirected graph. Like pretty straightforward question. Again, I'll give you guys like about three minutes to take a look at the question first, and then I will try to prove it in a more rigorous way. Quite intuitive, this answer, this question. Oh, I guess you just entered a, yeah, maybe next time we should probably figure out a better way to upload the files. Next time I'll upload the files like before the session. And let me give you the material. I just uploaded in the Zoom chat window. I didn't like expect people coming in different times, so my bad. Next time I will try to upload the files before the session starts. So right now we just finished like question 2. Then the answer is A and B, and we're now looking at question 3. Okay, let's take a look at the question together. Like we want to prove like there are an even number of odd degree vertices in any undirected graph. And so what is an undirected graph? Like very pretty simple. This is an undirected graph. Forgive me about my bad like handwriting here. Like the key point of this question is like, let me write it down. Suppose we have n total nodes. Suppose we have n nodes. Here, the key point of it is sum of all the degrees of these nodes equals to 2 times the number of edges. And we can just denote it as 2 times E. This is the key part of this question. And if you like understand this correctly and perfectly, then there's nothing hard about this question. We just assume that the first R nodes have even number of even are or maybe like are even number are even degree. Have even degrees. And from R+1 to N, these nodes have like odd number of degrees. So let's write it down here. So this is the first R, the sum of the first R, sum of the degree of the first R nodes. And this is the remaining. Let's try with another letter here. J. J. And from here, the proof is quite simple. This is even. This is definitely even. And here, this has to be even because even plus odd is odd, and even plus even is even. This whole sum here has to be even. And then our assumption is from like our assumption is from node R+1 to N, these nodes are odd degree nodes. So given that odd plus odd is even and odd plus even is odd plus even is odd. So there must be even number of odd degree nodes. Otherwise, this equation won't hold. So yeah, basically this is a solve process of the whole of this question. And this is what we want to see in your homework in terms of like proving. So are there any questions about this? Oh, okay, I'll stop sharing the screen here. Let's take a look at the next question. Question number 4. Like pretty straightforward. Again, like this week, this is just like let you recap on all the materials you learned previously. Again, I'll give you guys a few minutes, 3 to 4 minutes to take a look at it and think about it. No, the edges doesn't have to be even number of edges. Like we're asking is the number, because like even if like the odd number of edges, the sum of all the degrees, yeah, the number of edges doesn't matter here because like the sum of all the degrees, the sum of all the degrees of each node has to be even. Like the key point is here. Let me just share you on the subline here, number of sum of degree and v, because like for each edge, it connects two nodes like from one end to the other end. And so for if we understand like the concept of the edge, we will know that the sum of the nodes, the sum of the degrees of all the nodes is actually 2 times the number of edges. That's why like the number of edges doesn't matter here. Okay, let's if you like Peter, if you have any questions, like I would like to like in terms of question 3, I can answer your question after this session. But right now, yes, you're given like a set vertices and set edges in question number 4. This is basically what we want to like show like how to analyze the time complexity and maybe the space complexity, because like the professor probably didn't mention, he didn't mention a lot about like the space complexity, but that's a quite important part of the algorithm design and algorithm thinking. And so for the first question is, we want to transform, just a second. We want to transform an adjacency matrix to adjacency list. So like, let me make some assumptions about like all the nodes are from 1 to n-1, and we're given like a set adjacency matrix here. If we have like n nodes, all the nodes are from 0 to n-1. This is our first assumption. So let me try to figure out matrix to list, and we're given like adjacency matrix. So is it like is everyone comfortable with Python, or I'm not sure like what kind of like programming languages like you guys are comfortable with? I think I figure like Python is the closest to pseudocode, so that's why I use Python here. So I'll just keep using Python. So if you guys have any questions in terms of this programming language, I can switch to whatever you want. Just the one I know how to write it. And first, we want to find out how many nodes we have in this graph. So this is basically the length of the matrix, because we have like a 2D matrix where the number of nodes is actually the length of the matrix. And then we want to initialize the adjacency list that we want to transform this matrix to. Basically this. And right now we want to like traverse all the edges inside this graph. Inside this adjacency matrix. One of the key points is like in the lecture, like professor mentions that the professor didn't mention like the type we should use for the adjacency matrix, because there's no point using an integer matrix, integer array or integer list, because integer is like 4 bytes, while for like the status, the state between two nodes, it's either connected or not. So we don't need like so many states to represent whether two nodes are connected or not. So what we need is basically a 2D array or 2D list of booleans to indicate whether two nodes are connected or not. This way we can save like the space complexity. We can save the space for this algorithm. So basically here, this is a boolean. And if there's a connection between these two nodes, we would just add this. Basically, like we just like add the neighbor, put if there's a connection between I and J, we just want to add J to the neighbors of I and add I to the neighbors of J in the adjacency list. Very simple code here, and return the result here. And let's take a brief look at the time complexity we use here. So for the initialization part, we definitely need to go over all the n square elements here. So the initialization part, the time complexity is O of n square. And here, as you can see, there's a nested loop. So here, as you can see, there's a nested loop here. So the complexity is also O(n) squared. So generally, the time complexity of this algorithm, like that, it's O(n) squared. Now let's take a look at the the second question. Oh, my bad. Yeah, it's actually undirected graph. Yes. But like the idea is quite similar here, whether it's an undirected graph or a directed graph. It's just like if it's a directed graph, we don't have to like append the neighbors on both sides. Good question, yeah. So like let's take a look at the second one, list to matrix. Same as before, we want to know how many nodes we have. Like, so the adjacency matrix, the representation of adjacency list is like this. Just list of list, or we can say array of array, where each array represents all the neighbors that a node has. So as usual, we want to initialize this. Initialize a n by n adjacency matrix to represent all the connections between all the nodes. We'll initialize everything as false. That means like there isn't a connection, and we'll try to update it later. Here we initialize a n by n adjacency matrix, and the time complexity here is definitely O of n squared. And right now we want to traverse all the nodes first, and inside each iteration, we want to traverse all the neighbors of that specific node. So as usual, no, you cannot use I 2 times. Like, so here you have to use another J. That's basically because like inside this, for line 19. Oh. Thank you. typo here. So let me continue with this. Inside each iteration, we want to find out all the neighbors we have. This is basically all the neighbors that node I has. Oh, sorry, this is another. And we want to traverse all the neighbors of the node I has. So for undirected graph, maybe you guys think we need to do this again. But actually this can be neglected. This line of code can be ignored because when we're traverse a node, or when we're traversing outside here, when we're traversing the node neighbor here, we'll actually update the connection. Since the image in an undirected graph, the adjacency list representation is symmetric. If there's a connection between A and B, then B is the neighbor of A and A is also the neighbor of B. So this line of code can be actually ignored. And don't forget to return the result. And so here, this is basically the whole algorithm. Let's take a look at time complexity here. So time complexity from the outside of this, we will take n iterations. And from inside of here, we need to traverse, for inside each iteration, we need to traverse all the neighbors that node I has. So inside here, let's say that mi is the number of neighbors that node I has. So outside here, it is this here. So here, I think Professor covers this part in the lecture here. This the kind of complexity is O n plus m, where m is the sum of all the edges. Yeah, but given that in our initialization, the time complexity is O(n) squared, where n is the number of nodes, and we know that in an undirected graph, the maximum number of edges is n times n minus 1, which is O(n) squared. So basically, this algorithm is if we consider the initialization, this algorithm is the complexity of O(n) squared. So pretty straightforward. And also I see that the time is up, and I'll just mention one point before we end this session, that the professor mentions that the adjacency list, one of the disadvantage of adjacency list is that if you want to query, if you want to find out whether two nodes are connected or not, the query time will take O of n because it's a linked list. The data structure decides the time complexity for the query time. But what if we update this update this data structure a little bit? Instead of using linked list, we can try using maybe another data structure such as dictionary, where using dictionary, using map, using a hash map, or in Python using a dictionary, where inside each dictionary, inside dictionary, we have a set to represent all the nodes, all the neighbors that a specific node has. Basically, it's a map of set. Yeah. This way, we can, this way the space complexity is the same while we definitely reduce the time complexity of the query time. So I think this is like more like a better way to represent adjacency list using map, hash map of hash set to represent adjacency list. And this kind of question is, well, like frequently pop up in during interviews or during like exams. So like, thanks everyone. So if you guys have any questions, I will stay here for another minute or two to answer all the questions in terms of the homework or today's materials. Yeah, sure, no problem. Yeah, no problem. Yeah, let me like stop sharing my computer and I'll start sharing from my iPad here. So, what is the question again? You can jump on I mean you can jump on mic if you want. This way, like.
I just wanted to know what exactly if you were proving or disproving what the thing was saying. I just didn't understand what you were doing.
Okay. So like the thing here is like, so do you understand like what is the degree of a node? Like for like
Yeah,
here.
it's the number of edges.
Yes, number of edges it is connected. Yeah. So it's the number of edges it is connected with, right? So
Yeah.
like try to understand this line here. Like this is the key part of it.
Yeah, I get that, I think.
You get, yeah. So do you understand this line here? Like this part of it?
Degree plus. No.
Yeah. So what we do is we assume that like there are R nodes that have even degrees, and that means like the rest of the nodes have like odd number of degrees. Is that correct? Like, can you understand this part? Like, you assume
I think so.
some of them have even degrees, some of them have odd degrees. This is like a more abstract way of thinking about algorithm because, yeah, this is like a more abstract way. We assume like there are nodes that have even numbers of degrees, and while the rest of them have like an odd number of degrees. This is like the assumption we made. This R can be anything in terms of like the structure of like a graph or structure of, yeah, in terms of the structure of a graph.
Sure, but what does that prove? I don't
Yeah,
get
so
what that proves.
yeah, if so like there are if like there are R nodes, and then here is just 1 second.
Wait, so overall there's n nodes.
Yeah, overall there are n nodes, and the first R nodes, we assume like we just like basically we can assume that we sort all the nodes at the first place, and the first R nodes has have like all even number of degrees, and the rest of them, the remaining of them, has odd number of degrees.
So the first one in there, I equals 1 to r degree of vi is even, but then I equals r plus 1 to n, you're saying is also even? I don't understand that.
This is the sum of them. It has to be even because, as I mentioned here, this is like the summation we made here. This is like the summation here. So for each of them, each of the first R nodes, the degree is even, right?
Sure.
So the sum of them has to be even, right?
Yeah.
Yes, so this whole part is even, and the right side of this equation is even as well. And like very simple like math
Oh,
is, yeah, the even plus even has to be even, the even plus odd is odd. So this part, the summation of the
that
part,
one must be even.
yeah, that one must be even as well. I mean, the summation of this part has to be even as well.
And so that's what you're proving there, is saying that there are an even number of odd degree vertices.
Yes, yes, because odd plus odd is even, and even plus odd is odd. There has to be like even number of odd degree vertices. Otherwise, this equation won't hold.
Okay. Wait,
Yes.
but the whole thing is in that second part right there, where you're saying in the r equals I, from the summation I equals r plus 1 to n degree
Hmm.
Vj, that summation is even.
Yes, yes, the whole part, the whole thing, the whole part is even.
And that's what proves the question. It's not
Yes,
like the
yes,
rest of.
because like the next step is because degree Vj is odd for or j from r plus 1 to n. Yeah, this part, degree Vj, and some of them is even. The sum of all those, the sum of degrees of all those odd degree nodes are even.
Okay.
Yeah, so there must be even number of odd degree.
Okay.
Nodes. Yeah.
Uh, and you went over number 1 and number 2 in the first half of the
Yeah, yeah, number.
for the first 20-30 minutes.
Yeah, yeah, yeah.
Okay, I wasn't here for those, but okay.
Okay. Yeah, so
That's I can watch the recording. I'm assuming you guys are gonna put the recording up.
yeah, yeah, yeah. I record everything on the cloud. So, like for this for the second question, we don't require we don't require require you to write down the whole proving steps, but like I still prove it like during the discussion session. This is like the thought process we want like students to put in their homework when they are trying to solve like a proving question, like how to prove like a induction problem, something like that.
Okay.
Yeah.
And you went over all that. Okay. And then for number 1, and
Number
you
one is
said
just like homework and homework 0 and quizzes.
okay. That's fine.
Yeah.
All
Yeah.
right.
Okay.
Thank you.
Welcome.
Yeah.